Hey, welcome back. I'm glad you're still here. This is Charlie Thompson, and this is the intro video for the first part of Chapter 1, which is, weirdly enough, the second chapter in the book, but I don't want to talk about it. So, here's what we're going to be talking about. Solar energy, which is energy from the sun, seasons caused by energy from the sun, and the atmosphere. So this chapter is really... I would really divide it up into two chapters. There's solar energy and seasons, that's the first part, and then the second part's going to be on the atmosphere. So here's all the topics we're going to talk about, and let's look at the big questions because those are better. What's the origin and structure of our solar system? Fascinating. Not really super important geographically speaking. Geographers tend to be more concerned with things on Earth, but hey, where'd you get that nice planet? That's a good question for geographers. Why do we have seasons? We'll go through that. That'll be lots of fun. And what are the properties of our atmosphere? So there you have it. Sun, seasons, and our atmosphere. So we'll talk about the galaxy and the solar system, our galaxy, our planet, our solar system. Yeah, our solar system is made up of the sun and the planets, and our solar system is one of hundreds of billions of solar systems in our galaxy. This is an artist's representation of the Milky Way galaxy. Our galaxy is just one of hundreds of billions of galaxies in the universe, each galaxy made up of hundreds of billions of stars. We'll talk about energy from the sun. Energy comes in from the sun, interacts with our magnetic field. It makes the really beautiful northern lights, the aurora borealis, and the southern lights, the aurora australis. We'll talk about the different wavelengths of energy from the sun. We call that the electromagnetic spectrum. We'll look at energy that comes out of the sun, and we'll look at energy emitted by Earth. We'll talk about wavelengths emitted by the sun. We'll talk about energy coming into Earth, and then net radiation is the difference between the energy that comes in the yellow lines and the energy that goes out in the red lines. So overall, Earth's energy budget is more or less balanced. Because we've added fossil fuels, or rather because we've burned fossil fuels, we've put greenhouse gases in the atmosphere, and they absorb heat. So slightly less energy is going out to space than we get coming in, and that's causing Earth to warm. We will look at spatial patterns of net radiation. The pink parts, more energy comes in from the sun than goes out from that spot, and the purple places, more energy is leaving Earth from that location than is coming in from the sun at that location. We'll talk about the seasons. We'll talk about the 5 reasons we have seasons. We'll talk about the different seasonal events. We'll talk about what seasons actually means. And then we'll get to the atmosphere. We'll talk about what the atmosphere is made of, mainly nitrogen. We'll talk about the different layers of the atmosphere organized by temperature. So we'll talk about the troposphere and the stratosphere and the mesosphere and the thermosphere. We'll talk about the atmosphere's layers in terms of function, like what have you done for me lately? And the answer would be, well, absorbing gamma rays, X-rays, and ultraviolet radiation so you're not incinerated. That's pretty nice. Thank you, atmosphere, for that. As well as giving us oxygen to breathe so we don't suffocate. That's also pretty good. Yeah, we'll talk about the layers. We'll talk about the ozone hole, what that really means, why we care about ozone. We'll talk about variable atmospheric components. So the good stuff in the atmosphere more or less is fixed. The amount of carbon dioxide to oxygen to argon, those are pretty much constant. So the stuff that varies is pollution. So variable atmospheric components is a fancy schmancy way of saying wildfire smoke. Here's a recent map showing wildfire smoke coming off of the American West. We'll talk about different types of anthropogenic pollution. We'll talk about China and their air quality. These are 2 pictures taken on different days from the exact same location in Beijing. This is the Cuyahoga River. It's a river in Ohio, and in the 1970s, it used to catch on fire. It was so polluted, it caught on fire repeatedly. That led to the signing of the Clean Water Act and the Clean Air Act, and also the creation of the Environmental Protection Agency, all of that under the Nixon administration. And that's pretty much it for the chapter. So now you get a little bit of an overview. Let's dive in and at least get through the first section. I love this picture because, and let me see if I can get my pointer, because you can see just how thin, in fact, the atmosphere, on looking at the atmosphere sideways view of the atmosphere, it's actually thinner than the little red dot of my pointer. So when you get to that chapter in the book and you see that picture, you can just barely make out that incredibly thin line that is the atmosphere. That is all that we breathe. That is every place that we have weather. That's all that stands between us and raw radiation from the sun. So there's the topics. I'm not going to read those again. They're in the book. So concepts. Again, what is the origin and structure of our solar system? Where'd you get that nice solar system? Why do we have seasons? There's 5 reasons. And what are the properties of our atmosphere? What does it do? So, starting off with our galaxy and solar system. Our sun is a star, just like all the other stars that we see in the sky. The sun and our planets make up our solar system. Our sun is just one of 300 billion stars in the Milky Way galaxy. And then all the hundreds of billions of galaxies combined together make up the known universe. So here we've got a diagram showing our solar system, Earth, the third planet from the sun. There we've got the sun, we've got Earth, no Pluto. Pluto's a garbage planet. Here we've got a side view, or rather a top view, of the Milky Way galaxy. That is our galaxy. It is 100,000 years across at the speed of light. So if you turned on a flashlight here, it would take 100,000 years for the light to travel all the way across the Milky Way galaxy. That's just amazing. Given that the speed of light is 300,000 kilometers per second, or 186,000 miles per second. So traveling at a speed of 186,000 miles per second, it would take light 100,000 years to cross from one end of our galaxy to the other end. So our solar system condensed from a huge, slowly rotating, collapsing cloud of dust and gas. This is called the nebular hypothesis. Nebula means cloud. Gravity is the idea that mass attracts mass. And so over time, even though gas and dust doesn't weigh a lot, it has mass. And so gravitational attraction collapsed the dust and gas. Here's a video I've posted. The link is in your playlist, and it's also embedded in the lecture slides. I'm not going to watch it now. This is a different video. This is an outstanding video. It's on the Hubble Ultra Deep Field. The Hubble Space Telescope did 2 amazing projects. Once upon a time, they just pointed it at a random spot in the sky and left the shutter open for a week or so and to see what they would find. And they were amazed at how many galaxies that they saw. This is a second attempt. In this attempt, they pointed it at a dark spot in the sky, which would mean that there are few stars in our neighborhood. So they pointed it at a dark spot in the sky, left the shutter open for 10 days, and detected over 3,000 galaxies. The farthest or oldest is 13.2, I think about 13.2 billion years. So light from that galaxy had been traveling for 13.2 billion years only to end up on that satellite. It's a great video. It kind of puts the scale of our universe in perspective, just how tiny we are and just how incomprehensibly huge the universe is. Okay, speed of light is 300,000 kilometers per second. I already mentioned the Milky Way galaxy is 100,000 light years. A light year is the distance that light travels in 1 year. The known universe, we think, is 47 billion light years across. That's pretty darn big. Our universe is 13.7 billion years. The BY is an abbreviation for billions of years, LY, light years. So our universe is 13.7 billion years old. The oldest stars, the oldest galaxies that we've seen are 13.2 billion, because that's how far away they are. So it took the light that long to reach us. So when you look up at the sky and you see stars, it's entirely possible many of them are gone. Like the nearest star to us, I think it's Alpha Centauri. It's about 4 light years away. So it takes 4 years for the light from that star to reach Earth. So if it blinked out today, we wouldn't know for 4 years. So if there's a star that's 100 million light years away, if it blinks out, it's going to take 100 million light years for that light to reach us. Earth and our solar system is about 4.54 billion years old. I put that in bold because you need to memorize that. Earth and our solar system, about 4.54 billion years old. So our universe, the Milky Way, let me back that up. The universe is about 13.7 billion years old, so our solar system is like a third of the age of the known universe. So it's relatively new. Even though it's over 4 billion years old, it's relatively new, speaking in terms of the entire universe. Average distance from Earth to the Sun is 150 million kilometers. We are about 5 million kilometers closer in January. It takes light 8 minutes and 20 seconds to reach us from Sun to the Earth. So again, if the Sun blinked out or exploded, we wouldn't know for 8 minutes and 20 seconds. The orbit around the Sun isn't a circle, it's an ellipse. Energy from the Sun. Solar activity, the sun is 99.9% of everything in our solar system. It is massive. Literally, it's massive. It's huge. It's 99.9. In fact, I think it's even 99.99%, but 99.9 is close enough. It's almost everything. It is so big that gravitational attraction inside it is so massive that every second 4.5 million tons of hydrogen are converted to pure energy, light and heat. 4.5 million tons of physical matter becomes pure energy every second inside the Sun. So down at the bottom, this diagram is showing energy from the Sun. The average amount of energy that we receive from the Sun at the top of the atmosphere is about 1,366 watts per meter. You can see it fluctuates on an 11-year cycle by, half a watt, less than a whole watt out of 1,300 watts. Every now and then people say, well, maybe Earth is getting warmer because there's more energy from the Sun. Yeah, no, we're kind of in a slumpy phase right now with just ever so slightly less energy from the Sun. So the Sun produces mainly light and heat. It also produces clouds of electrically charged particles. So it takes 8 minutes for light to reach us. It takes a week for these particles to reach us. They are called the solar wind. On the Sun, there are magnetic storms. Those are sunspots. They look dark, but they're actually emitting more energy than the rest of the surface. There's an 11-year cycle between the maximum and minimum energy coming out from the Sun. That's the solar cycle. Yeah, it's just a cool picture of the Sun. The Sun is gorgeous. Earth is tiny. In fact, my little pointer dot is way, way, way bigger than the size of the Earth. You can see a solar flare in perspective to the relative size of Earth. When you look at the textbook in figure 1.3b, look for the smallest dot that you can find on the surface of the Sun, and then think about the fact that Earth is smaller than that dot. So the solar wind interacts with Earth's magnetic field to make auroras. Earth's magnetic field is generated by the motion, the swirling, the dynamo-like action of Earth's molten iron outer core. The inner core is solid iron. The next layer out from the inner core is the outer core. The outer core is made up of molten iron, and it spins around, and as it spins around, it generates Earth's magnetic field. When the solar wind interacts with gases in the atmosphere, they get excited, then they glow just like a neon lamp. These yellow lines are lines of magnetic force. So these are lines of magnetic force. This is demonstrating the sort of bubble shape of Earth's magnetic field. Earth's magnetic field shields our atmosphere from being stripped away by the sun. If we didn't have a magnetic field, Mars, for example, does not have a magnetic field. You know what else they don't have? They don't have a breathable atmosphere. So it's entirely possible we could terraform Mars. We could somehow manufacture something that would generate enough oxygen that we could breathe on the surface of Mars, but without a magnetic field, that energy from the sun, the solar wind, it's gradually just going to strip away the molecules in the atmosphere on Mars. So it's a really, really, really good thing that Earth has a magnetic field. Not only does it make these really gorgeous lights at night, the auroras, here you can see the auroras over Canada. I'll put up a nice tourist video into the lecture slide video links because they flicker and dance in these big sheets in the sky in the nighttime. Here you can see them around the South Pole. They're around the South Pole, also around the North Pole. And we're up to 1.3 already, the electromagnetic spectrum. So the electromagnetic spectrum is all the energy that is emitted by the sun. The spectrum of all possible wavelengths of electromagnetic energy. Solar occupies a portion. So wavelength is the distance between 2 points on any two successive waves. I hope I have a picture. Frequency is the number of waves passing a point in 1 second. The shorter the wavelength, the higher the frequency. The hotter the object, the shorter the wavelength. So, anybody out there a blacksmith? Anyone? No, I'm just kidding. I can't see your hands. This is a video. Anyway, if you were a blacksmith, you would know what temperature metal was based on the color. Like normally metal doesn't glow. You got to heat it up before it starts glowing. But then when it gets hotter, it's going to start to glow red. As it gets hotter, it's going to glow orange. As it gets hotter, it's going to glow yellow. And eventually, if it gets hot enough, it'll glow white. So the color of an object tells us the temperature of an object. So the hotter the object, the shorter the wavelength. Also, the hotter the object, or rather, the shorter the wavelength, the higher energy for that wavelength. The energy emitted by the sun, for the most part, is right around 0.5 micrometers, which is smack dab in the middle of the visible spectrum. So most of the energy from the sun, if you looked at the midpoint of all the different frequencies coming off the sun, the midpoint's about 0.5 micrometers. If we were going to break it down, the energy coming out of the sun, about 8% of the energy from the sun is in UV, X-ray, and gamma. That's very dangerous energy. Those are very short wavelengths, very high energy. Ultraviolet light will blow apart the DNA in your skin. X-rays go through bone, higher energy. So about 8% UV, X-ray, gamma. 47% is visible light. So I will keep talking about shortwave. I'll try to use both terms. Visible light is shortwave energy. When we geographers talk about shortwave light, we're referring to visible light. Long wave is infrared, which we feel is heat. So 47, 45, 8. Most of the energy coming out of the sun is right here in the visible spectrum. Surface temperature of the sun is about 6,000 Kelvin. The energy coming out of Earth, because Earth is cooler, it's emitting longer wavelengths. The energy coming out of Earth is centered around 10 micrometers. So the wavelengths of light coming out of Earth are about 20 times longer than the wavelengths coming into Earth. So if we were in class, we would spend so much time on this diagram. It's one of my favorites. I love this diagram. But you know, this is a video, so I can just talk as long as I need to cover everything. This is an ugly diagram. It is a frightening diagram. It's an imposing diagram. I will now attempt to make sense of the diagram for you so that you can enjoy it. So across the side, so the y-axis is watts per square meter at different wavelengths. So 2 watts, 5 watts, 10 watts, 20, 50. I believe that's a typo. I think that should be 100. But in any event, this is, you can see that it goes 2, 5, 10, 2, 5. I think that should go 2, 5, 10, and then 2 again, 2, 5, 10. But the point of all that is, as you go up, it's not linear. Going from 2 to 5, going from 5 to 10 to 10 to 20. It increases faster and faster as you get into the higher energetic parts of the spectrum. So along the side, the higher it is, the higher the energy is. Across the bottom, we have the shortest wavelengths, 0.1 micrometers, to the longest, 10 and 15 micrometers. So again, 0.5 micrometers, that's the center of the visible spectrum. And then 10 micrometers, that's about the center of the energy coming out of Earth. Okay, so far so good. Next up, we got the purple and the yellow, that's energy from the sun. And the orange and the white, that's energy coming out of Earth. So the purple line represents energy received at the top of the atmosphere. You can see it's a bell-shaped curve. If the sun got hotter, it would shift towards the ultraviolet. The peak would get higher because if the sun was hotter, it would put out more energy, and the energy that it put out would be concentrated in the shorter wavelengths. As the sun ages, it's going to get cooler, so what's going to happen is it's going to shift from yellowish to reddish over time, and the energy it puts out will be lower, less energy as the sun cools off over billions of years. So the purple, energy from the sun at the top of the atmosphere. So the purple line is the energy from the sun that's hitting the top of the atmosphere. The yellow is energy from the sun that makes it to the surface. So this is how much that comes in from the atmosphere in the visible spectrum. This is how much makes it to the surface. So the gap between the energy hitting the top of the atmosphere and the energy making it to the surface, if there's a gap, that means that energy was absorbed by the atmosphere. So let's look at some of these big windows or gaps in the curve. So we've got a huge gap over here in the ultraviolet. You can see over 150 watts coming in the ultraviolet region, but only 10 are making it to the surface. So the rest of it is being absorbed by ozone in the atmosphere. And over here, you can see like nothing shorter than 0.2 micrometers is making it in. All of it's getting absorbed by ozone in the atmosphere. Over here, we've got greenhouse gases absorbing longer wavelengths. In fact, the visible spectrum goes from 0.4 to 0.7. Anything longer than 0.7 we can't see. Anything shorter than 0.4 we can't see. So the visible spectrum is really narrow. Longer than that, this is infrared, this is heat. So we've got greenhouse gases, again, over 150 watts coming in, but only 10 are making it to the surface. And that's because carbon dioxide, water vapor, other greenhouse gases are absorbing that heat energy. So it's not making it to the surface directly. That's it for energy from the sun to the top of the atmosphere and then to the surface. And then this orange line is energy leaving the top of Earth's atmosphere, and the white line is energy leaving Earth's surface. So 2 watts are leaving Earth's surface, right around 5 micrometers, but barely anything is making it to the top because carbon dioxide is absorbing that. Right here, this little notch right here is water vapor. So water vapor absorbs heat. Water vapor is a greenhouse gas. Water vapor absorbs and radiates energy at a wavelength of about 12 micrometers. So satellites are looking, they have sensors that are sensitive in the 12 micrometer band. And the more energy being released in the 12 micrometer band, the more water vapor is in the atmosphere. So you can use the energy coming off of Earth or coming off of Earth's atmosphere in the 12 micrometer band to tell how much water there is in Earth's atmosphere. Because when water releases heat, it's releasing that energy at right around 12 micrometers. Love this diagram. All right. Next up, we got the whole electromagnetic spectrum. It's about 2 quadrillion times the difference between the smallest wavelengths emitted by the sun and the longest wavelengths. It's a difference of about 2 quadrillion, of which we see from 0.4 to 0.7. So it would be as if you had a piano with 2 quadrillion keys. It would be a very long piano. And you could only hear the one key right in the middle. The key right next to it, it's too high. Dogs can hear it, but I can't hear it. And in this case, actually, these are longer. Sorry, my bad. So the key right next to it, this piano's backwards. These are the lower notes. These are the higher notes. So this note, ultraviolet. Yeah, bees can see ultraviolet. Birds can see ultraviolet. We don't really see ultraviolet. Infrared, we feel heat, but some animals like pit vipers, some types of rattlesnakes can actually detect infrared heat energy. So we don't see anything but 0.4 to 0.7, but it's really interesting because that's the peak, almost as if, well, humans evolved on a planet that had a sun with a temperature of 6,000 degrees. So if you had an organism from another universe, another galaxy, if you knew what frequencies of light their eyeballs, if they had eyes, whatever ocular organs they have, if you knew what frequencies their ocular organs were sensitive to, you would know what temperature their sun was. That's kind of fun. Okay, back to this. So, too long, didn't read, I'm sorry, you're talking about wavelengths. Light comes in from the sun, gets converted to heat, the heat goes out to space. The longer the wavelength, the lower the energy. Like AM radios have a wavelength of about 1 kilometer. FM radios have a wavelength of about 1 meter. Microwaves are from centimeter to millimeter. From millimeter down to micrometer is infrared. And then we're getting into really short stuff. Ultraviolet breaks apart DNA. X-rays go through bone. I don't even know what stops gamma rays. Ooh, that's a good place to stop. I'm just going to break this up. I'll record 1.4 and post it separately so that it's not like a 4-hour long video that's completely overwhelming. Anyway, good luck with sections 1.1 through 1.3.